In this video, I want to take a look at solutions to Euler equations on the negative side. Right? Everything we've done so far with Euler equations, we've assumed that x is positive. And we do this because we're going to be dealing with functions x to the r. And if r is not an integer, it's tricky to say what you mean by raising a negative number to that power. For instance, the half power. What is negative 1 to the half power? Well, it's I, right? It's an imaginary number. And we can work with those imaginary numbers, but when we're looking for real solutions, we're looking for real functions, we don't want to be throwing negatives into square roots. So what actually is happening on the negative side? So let's take a look. If x is negative, what I'm going to do is I'm going to let u equal negative x. So u will be positive. Now I want to rewrite the differential equations in terms of u rather than x. So I've got to take a look at a few things here. Right? In that second order differential equation, you certainly have the derivative of y with respect to x. You also have the second derivative of y with respect to x. But here, let's take a look at the first derivative. And I know that the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. This is the chain rule. If you're thinking of y is a function of x and x is a function of u, then you can find the derivative, or actually I guess the other way around. U is a function of x and y. Anyway, the two are related. dy dx and dy du are related by the chain rule. And what I know here is, because of the substitution that I'm talking about here, that the derivative of u with respect to x is minus 1. And so the derivative of y with respect to x is going to be minus the derivative of y with respect to u. This makes sense to me in that if think about something as x is increasing, let's say it's going uphill. Well, if you're taking the derivative with respect to minus x, that is, you're going in the other direction. Well, if you were going uphill in this direction, then you're going downhill in that direction. And sure, the slope should just be minus for whatever it was. Now, the second derivative of y with respect to x this is just notation here, derivative with respect to x of the derivative of y with respect to x. That's the second derivative. But what I know is, again, the chain rule. How do I take the derivative with respect to x? I could first take it with respect to u, but then multiply by du dx. However, we've just established up above that dy dx is equal to minus dy du, and we've established that du dx is equal to minus 1. So what this tells me, those minus signs cancel out, and that what's left is the derivative with respect to u of the derivative of y with respect to u. That would be the second derivative of y with respect to u. So the second derivative of y with respect to x is equal to the second derivative of y with respect to u. Again, this makes some sense to me because the second derivative, remember, is telling you about the concavity. If this thing's bending upwards or downwards. Well, if you're moving across it this way and you're seeing it bending upwards, or if you're moving across it the other way, you're still bending upwards, right? That concavity is still positive, no matter which direction you're going. So, what I'm going to do now is I'm going to take my Euler equation, and there's my standard Euler equation. And I want to rewrite it in terms of u rather than in terms of x. So, first of all, I'm going to replace these prime notations, derivatives, with what they actually are. I use prime notation when there's no question as to what the independent variable is. When I just say take the derivative, it's like, well, there's only one independent variable. Well, now it's not quite that because I have x and u both acting as independent variables, and I need to know which one I'm taking the derivative with respect to. So the initial differential equation was all in terms of derivative with respect to x. So that's the way I write it. So now I'm going to replace my x's with minus x's and those derivatives with what we just calculated they were equal to. So the x's are going to be replaced by minus u's, right? So this x is being replaced by a minus u. This x is being replaced by a minus u. This second derivative of y with respect to x, I'm replacing with the second derivative of y with respect to u because they are equal to each other. But this derivative of y with respect to x is actually minus the derivative of y with respect to u. And the y is still y. Notice what happens here, that when you take minus u and square it, you just get u squared. And when you multiply this times that, the minus signs go away, and we end up with this equation. So this first equation here I've called star, and this new equation I call diamond. But notice they're really the same equation. It's just that the u is replacing the x. So that if I have a solution to the first equation, star, that looks like y equals x to the r, then I would claim that I have exactly the same solution, only with u as the variable, y equals u to the r, to this second equation. But u to the r is just minus x to the r. Which is telling me that what do I do on the negative side? I just make it positive and then end up with the same result. Well, that would be take the absolute value. So my solutions, instead of saying x to the r, I should be saying absolute value of x to the r. And the final result here, the bottom line, is that there were three situations I might be in. If the quadratic equation had two real solutions, then here's what I would say the general solution looks like. C1 absolute value of x to the r1 plus C2 absolute value of x to the r2, where r1 and r2 are the two real solutions to the quadratic equation. If there's only one solution to the quadratic equation, then I do this. C1 absolute value of x to the r1 plus C2 absolute value of x to the r1 times natural log of x. Sorry, natural log of the absolute value of x, right? We just absolute value all the x's in sight to handle what's happening on the negative side. And lastly, if you had complex conjugate roots to that quadratic equation, so a plus or minus bi, then my solutions would look like the absolute value of x to the a times the quantity here, c1 cosine b natural log absolute value of x plus c2 sine of b natural log absolute value of x. Okay. Now, this is not actually the whole picture, but it's at least a better part of the picture. It tells you what to do on each side, positive x's and negative x's. The thing that bothers me about it is that, I mean, the very first example I did, we ended up with like x and x to the sixth power, I think, you know, as my solutions. And it's like, I didn't have to worry about negatives on that one. Why would I take the absolute value? And so I want to take a look at some graphs here and see that there's actually a little bit more going on than just throwing absolute values around this. Let me pause here for a moment and switch apps. Let's take a look at this differential equation right here. The corresponding quadratic equation would be r squared minus 3r plus 2 equals 0, which factors into an r minus 1 and an r minus 2. And so my solutions would be r equals 1 and r equals 2. And so according to what I just did, well, according to what I did in the first video on these equations was I would have said y equals x to the 1, or c1 x to the 1, plus c2 x squared. Now I'm saying y equals c1 absolute value of x plus c2 absolute value of x squared. And that absolute value does absolutely nothing, because when you square it, whether it's positive or negative, you're coming out with a positive. And this bugs me, and I have to think this through every time. I'll admit, I don't use differential equations much in the math that I do on my own for stuff I'm doing. And so when I get to this point in this course, it's like, how is it that, okay, so suppose C2 is equal to 0. So let's just handle this x thing, right? So I'm looking at this saying, I think this is the solution to that differential equation, y equals x. And this is telling me, no, you should have this. And it's like, how does that work? How can there be two different solutions? What is it? There doesn't seem to be anything wrong with negatives here being plugged in for x, so why do I need to absolute value it? And the answer is because x equals 0 was a singular point. These are both correct. Notice that if x is a solution, then any scalar multiple of x is also a solution, because this was a linear equation. So y equals x would be a solution, but also y equals minus x would be a solution, because you just multiply by minus 1. So this right here coming down through that way would also be a solution. Or if this was the case, if I was using the absolute value of x, then okay, well then minus 1 times the absolute value of x would also be a solution. So the thing is, are you taking this piece and this piece together as a single solution, or are you taking this piece and this piece together as a single solution? Okay. The existence and uniqueness theorem says if you had an initial condition, that there is one and only one solution that passes through it. So if I was looking at this point here with this slope, right, would it be y equals x? That's the solution, or would it be y equals absolute value of x? That's the solution. And the answer is yes, both of them are, and it does not get in the way of it doesn't contradict the theorem, because the theorem says in the intervals where p and q are continuous. Well, notice to get p and q, I'd have to divide both sides here by x squared. So I'd have y double prime minus 2 over xy plus 2 over x squared. Sorry, that was a y prime. Y equals 0 divided by x squared, which is 0. And notice that at x equals 0 and at x equals 0, there's discontinuities in those things. So when I look at an initial condition here, the biggest interval I would expect to find continuity on is from 0 to infinity. And what happens on the other side of that asymptote, well, it doesn't happen to be an asymptote necessarily, but on the other side of that singular point, I have no idea. I could do it differently on each side. In fact, I could say, here's like this on one side and that on the other side, because I could shift at different amounts. I wouldn't change the derivatives. It's like as well when we do what's the integral of 1 over x dx, right? We usually say it's the natural log of x plus c, which isn't really, natural log of absolute value of x plus c, which isn't really the whole picture, because this is insisting that the answer be symmetric about the y-axis, and the plus c is just going to move that up and down, right? It'd move the whole thing up there, right? But it could be that you shift the two sides, so you could have the log here and there. You could shift them different amounts. Shifting vertically doesn't change the derivative, so this solution would be just as valid as this solution over here, any of those. So because there's a singularity at x equals 0, right? 0 is a singular point in this problem. We don't expect anything to be predictable from one side of the singularity to the other, right? That you can shift by different amounts, you can multiply by different constants on different sides, because if you had an initial condition, the only part that's really important is the part that's on the side of the singularity, same side of the singularity that your initial condition is on. Okay. So anyway, yes, both this is correct and this is correct. In the event that you've got integer exponents, it doesn't matter whether you throw those absolute values in there or not. If you don't have integer exponents, then yeah, you probably should. But even still, it's not really the whole story, because you could be shifting still different amounts on the opposite sides of that. You could have a different C1 on ones for positive x's than you have for negative x's, and it would still be okay. Anyway, there you go. There is the picture of what the solutions really look like. One more comment though. I used this same textbook, Boyce and DePrima, when I took the class many years ago, 1987 or 8-ish, something like that. And the teacher, was the same book, and in this section, for whatever reason, they used this Greek letter, I can't even draw it, the Greek letter C. I got so that if I was teaching this in class, what I would do is I would use this. It's a lightning bolt. Actually, it's a flat top lightning bolt, so it's a Shazam. So when you're reading a textbook in this section and they use these whatever these Greek letters are, it's just so many curlicues in it I can't draw it. I used a U in this video instead. But in class, if I did this in person, I would use a Shazam as my variable instead of U. Anyway, have fun. As I was editing this video, I noticed something I said about this picture right here that wasn't actually correct. I was talking down here about choosing different values of c on one side of the asymptote or another to shift different amounts. And it's similar to what I was trying to say up here, except that the c's here aren't shifting. I could pick different c's on different sides. So rather than saying shift it up, because this is actually wrong, you can't do that. But what you can do is you could have one slope on one side, and you could have a completely different slope on the other side, right? Which is essentially what we're doing with the absolute value, because you have a slope 1 here and you have a slope -1 there, or you have a slope 1 and a slope 1, right? As you switch from one side of x equals 0 to the other side, what value of c are you using? And the thing is, you can choose any one you want. But the correction I needed to make was, it's not the choice of a different c isn't shifting that side. It's just, it's being used here as a multiplier, so it's changing the slope of that side, right? Anyway, there you go. Have more fun.